In the previous lecture, we have started to deal with the problem of motion of a symmetric top under the action of gravity. And in the first part of this lecture, you have seen the basic theory for this symmetric top. Okay. Now, I have told you in the first part of the lecture, when we have obtained the final result, which I have mentioned here too, that the solution of the final result obtained in the first part is not possible easily, because that result actually involves the elliptic integral, and therefore we need the some alternative way in which the phenomenon is dealt in a qualitative manner. So today we are going to see the particular situation when we can discuss this problem easily. Okay. You can see I have shown this figure, which you have also seen in my first lecture on this motion of symmetric top under the action of gravity too. Here a symmetric top has been shown, which actually rotates about the symmetry axis, which is here this OZ dashed axis. Okay, and at any moment of time t, this symmetry axis is inclined to this fixed vertical axis, that is OZ axis, by the angle theta. Okay. Now, for the discussion of these particular situations, actually we will need the results which we have obtained in our first part of the lecture on this subject. So for your convenience, you can see I have mentioned all the important results which we have obtained in the first part of the lecture. Okay. You have seen, first of all, we have obtained the Lagrangian for this system. And you have seen earlier that the expression for Lagrangian L is given as 1 over 2 I1 times theta dot square plus phi dot square sine square theta plus 1 over 2 I3 times psi dot plus phi dot cos theta whole square minus mgl cos theta. Okay. Although this expression for Lagrangian will be not needed in this present lecture, but I have mentioned it here. After that, you have obtained the three integrals of motion. The first two integrals of motion were p psi and p phi. Here p psi is actually the generalized momentum corresponding to the cyclic coordinate psi, and p phi is the generalized momentum corresponding to another cyclic coordinate phi. You have seen that psi and phi, which are actually Euler's angles, they were behaving just like cyclic coordinates, because the expression for this Lagrangian L, you can see, does not involve psi and phi explicitly. So Lagrangian of this system is not an explicit function of psi and phi, so we call psi and phi as the cyclic coordinate in this present situation. And so we have defined p psi and p phi, whose expression I have written here, and these are the first two integrals of motion. And you have seen that this p psi is given like this. This is I3 times psi dot plus phi dot cos theta, and you have seen earlier that this psi dot plus phi dot cos theta, this is equal to omega 3, and therefore it is written as I3 omega 3, and which we have assumed that this is equal to I1 times A, where A is a constant. Actually, this is a very important result which will be needed in this present lecture too. The another integral of motion was p phi, whose expression is given like this, and this has been assumed as I1b, okay, where b is another constant. After that, we have obtained the expression for phi dot, which was like this. This is b minus a cos theta over sine square theta. This result is also very important for the present lecture, okay, and we will need to use this equation. And psi dot is given by this, although this for this result will be not needed in this present lecture. After that, you have seen that since the top is moving here under the action of gravity, and you know gravity is a conservative force, so this is a conservative system, and it is a well-known fact that the total mechanical energy of a conservative system remains constant. It is independent of time and position. So in this case too, the total energy E, which is T plus V, that remains constant. And the expression for total energy we have obtained in our previous lecture, and you have seen that if E is the total mechanical energy of this system, then E minus 1 over 2 I1A whole square over I3, which we have denoted by the symbol E dashed, is equal to this much. This is 1 over 2 I1 theta dot square plus 1 over 2 I1 times B minus A cos theta whole square over sin square theta plus mgl cos theta. Actually here, you know, this first term, that is 1 over 2 I1 theta dot square, this is actually kinetic energy, okay, and the sum of the last two terms, this represents the potential energy. But you know, in this gravitational field, the gravitational potential energy of this symmetric top with respect to the fixed point O is simply mgl cos theta. So this due to the presence of this extra term, that is 1 over 2 I1 plus times B minus A cos theta whole square over sin square theta, this sum of the two terms is known as effective potential. Okay, this is called effective potential energy or effective potential. So the expression for effective potential, which is denoted by the symbol V of theta, is given like this. This is actually the most important result for our present discussion. So you should remember it because you have learned it in the first part of the lecture, but the starting equation of the present lecture is this equation. Okay, I will start my today's lecture writing this equation. Okay, so this is the most important. And after that, you have seen that when we take the integral of dt between 0 and t, then this is equal to integral of d theta over 2 over I1 times E dashed minus V of theta whole to the power half 1 by 2 between the limits theta when time t is 0 and theta when time t is equal to t. Now after looking at this integral, it is obvious that theta is equal to theta of t. It means you can see that this equation in principle can be solved to obtain theta as a function of time. That is, we can obtain theta equal to theta of t. However, the solution for theta as a function of time involves the use of elliptic integrals, and the procedure so becomes very complex. Okay, so due to the complexity for the evaluation of this integral, due to the presence of elliptic integrals, we discuss this problem in alternative way, which deals the phenomenon in a qualitative manner. Okay, so now let us simplify the problem considering some specific condition. And so first of all, we are going to see the case of steady precession. Actually, I have told you in my first part of the lecture that this top performs or executes three types of motion: precession, nutation, and spin. So when this steady precession will take place, what are the conditions, how this steady precession takes place, how precession is possible without nutation, everything we will now discuss. And as I have told you that for this our starting equation will be the expression for the effective potential V of theta. And you have seen that this effective potential V of theta is equal to this much. This is I1 over 2 times B minus A cos theta whole square over sin square theta plus mgl cos theta. Okay. First of all, we will see the graphical plot of this V of theta. It means we will plot the effective potential V in against of theta, because you can see that this V is a function of theta. Now see, if you will take theta equal to 0, if theta is equal to 0, what will be sin theta? Sin theta will be equal to 0 when theta is equal to 0. And if you will take theta equal to pi, then again you know sin pi is also 0. So for theta equal to pi, sin theta is again 0. So if you will put here at the place of this sin square theta 0, then your result for V theta will be what? That will be simply undefined, infinite. Because after dividing by 0, the result will become undefined. Okay. So definitely the physically accepted solution, when we will plot V against theta, then you are seeing that V is infinity at theta equal to 0 and theta equal to pi. So you can say that physically acceptable range for the graph is what? For the graph, the physically accepted range will be 0 less than theta, and this is less than pi. This is the physically accepted range for theta in which the physical solution of this equation can be obtained. Okay. As you can see, when theta is 0, then the tangent to this curve will be parallel to the v-axis, and when theta is pi, then again this tangent is parallel to this v-axis, and therefore at these two values of theta, v becomes infinite. Okay. Now you can see that we must have at least a minimum in the energy diagram for some value of theta naught. This is actually the point of minima. Okay. And for any energy value, let us say E1 dashed, that is E dashed equal to E1 dashed. For this, you can see there are two values of theta. A line, this dotted line, which has been taken corresponding to E equal to E1 dashed. You can see this line actually intersects the curve at 2 points, at A and at B. And corresponding to A, the value of theta is theta 1. And corresponding to point B, the value of theta is theta 2. Okay. So actually the motion is limited between theta equal to theta 1 and theta equal to theta 2 for this value of energy E1 dashed. Okay. Actually, what does it mean? In fact, this result actually shows that the symmetry axis OZ of the rotating top can vary its inclination theta to the vertical axis Z such that this theta 1 is less or equal to theta and this is less or equal to theta 2. So if you consider that this is your vertical axis, which is fixed space Z axis, and this is the axis of symmetry, which is Z dashed axis, okay, then the top may orient in this direction where this theta will be theta 1, or in this direction where theta is equal to theta 2. Okay, and this angle actually corresponds to theta naught, which is fixed. Okay. In fact, in this condition, as I have told you, that the symmetry axis, this OZ dashed, okay, OZ dash of the rotating top can vary its inclination theta to the vertical this z such that this condition holds. Okay. So actually in this case a particular type of motion this top is performing, and this is called actually nutation. Okay. Now in the special case you can see if the energy E dashed is equal to E naught dashed, which actually correspond to the minimum value of the potential. Actually in this condition you can see that potential is minimum and the value of theta is equal to theta naught. Actually this value of theta equal to theta naught is constant. Okay. So corresponding to this energy the precession angle theta remains constant. So you can say that this is the case of steady precession. This is the case of steady precession in which the symmetry axis of the top or describes a right circular cone about the vertical axis z. Okay. And this is also called the precession without nutation. Such a motion is called precession without nutation. Okay. And therefore we will now discuss this the first of all this special case a little bit detail and later the general case. Okay. So I have mentioned all those facts here you can see, and now we are going to see in very detail the case of precession without nutation. Okay. So now let us see. As you have seen in the graph that when theta is equal to theta naught then V is minimum. So I have written V equal to V minimum. And in accordance with the concept of maxima and minima, you have definitely learned that if V is minimum for theta equal to theta naught, then definitely the first order derivative, that is dV by d theta at theta equal to theta naught, must be equal to 0. Actually taking this condition for minima, we can obtain the value of theta naught. Okay. So let us evaluate this result, that dV by d theta when theta is equal to theta naught is equal to 0. Now you know this is the expression for V. Okay. So I have substituted here the expression for V, and this will be equal to 0 when theta is equal to theta naught. Okay. Now let us differentiate this expression inside this square bracket. This is a very simple differentiation, you can do it, but I have actually differentiated it and I have done the algebra here. You can see here when the operator will be operated on this first term, then I1 over 2 is a constant factor, so it is at each. Okay. Now you can see the function which will be differentiated is b minus a cos theta whole square over sine square theta. Okay. Here actually there is a product of two functions. The first one is b minus a cos theta whole square and another is 1 over sine square theta. Okay. So we will use the product rule for its differentiation. So first of all take 1 over sine square theta at each and differentiate b minus a cos theta whole square with respect to theta. What will be the result? You can see this is just a function of function. First of all this will be 2 times b minus a cos theta. Okay. And after that we will differentiate this b minus a cos theta with respect to theta. B is a constant, so its derivative will be 0, and when you will differentiate a cos theta, that will be minus a sin theta. That minus and the minus present here earlier, that will become plus. So this is simply plus a sin theta. Okay. Now we will take this b minus a cos theta whole square at each and we will differentiate 1 over sine square theta. And what will be the derivative of 1 over sine square theta with respect to theta? This will be minus 2 over sine cube theta times cos theta, you know. And after that, derivative of this mgl cos theta. Mgl is a constant factor, and that of cos theta, it is minus sine theta. So the last term is minus mgl sine theta. And that will be equal to 0, but when theta is equal to theta naught. Okay. Now we will substitute theta equal to theta naught in LHS of this equation. But before that, let us see this 2 and this 2 will cancel out. This sine theta will also cancel out. Okay. And this 2 and this 2 will also cancel out. Okay. And after substituting theta naught instead of theta, our result is what? This is I1 times A times B minus A cos theta naught over sine theta naught. Okay. And minus I1 times B minus A cos theta naught whole square times cos theta naught over sine cube theta naught, and minus mgl sine theta naught equal to 0. Okay. Now let us take this minus I1 over sine cube theta naught as a common factor. Okay. Then the remaining terms will be what? This will be B minus A cos theta naught whole square times cos theta. I have written the second term here first. Okay. Since minus has been taken as a common factor, so sign of the above terms will be just reversed. And the next term is A sine square theta naught times B minus A cos theta naught. Okay. And the third term will be mgl over I1 times sine 4 theta naught. Okay. And that will be equal to 0. Now, since this I1 over sine cube theta naught cannot be 0 for all values of theta naught, therefore, definitely the term, the expression inside the square bracket must be equal to 0. And therefore, I have written this expression in this manner. This is cos theta naught c square minus A sine square theta naught times c plus mgl over I1 times sine 4 theta naught equal to 0. Here actually I have substituted c for b minus a cos theta naught for simplicity. Okay. So writing c instead of b minus a cos theta naught, our result becomes like this. Okay. Now you can see this equation 1. If you will see this equation 1 seriously, you can easily recognize that this equation 1 is a quadratic equation in C, and so its solution or its roots can be given by the formula which you know for the quadratic equation. So the solution of this equation 1 can be written as C equal to, you know, the formula is minus b plus minus root over b square minus 4ac divided by 2a. Utilizing that very formula for the roots of quadratic equation, what will be the values of c? This will be at the place of b, you can see there is minus a sine square theta naught. So minus minus will become plus. So this is a sine square theta naught plus minus b square. So this will be a square sine 4 theta naught minus 4ac. A is cos theta naught and c is this much. So this is 4 mgl over I1 times sine 4 theta naught times cos theta naught whole to the power half and divided by 2a. A is cos theta naught. Okay. Now you can take this a square sine 4 theta naught as a common factor, and after when you will take it outside of this square bracket, this will be a sine square theta naught because here there is a square root, and that a sine square theta naught is taken as a common factor from all terms. So this result for C can be written as a sine square theta naught over 2 cos theta naught times 1 1 is at the place of this, okay, because it has been taken as a common factor, and plus minus here there is also 1, okay, and 1 and minus 4 mgl cos theta naught over I1 a square, okay, I1 a square, because you have taken a square as a common factor, but this second term does not contain a square, so you must divide it by a square, okay. So these are the roots of the quadratic equation defined in equation C, and you can see C will have actually two values taking this plus minus sign, okay. But when you see this equation 2 which defines C, it is obvious that C is a real quantity, because C equal to B minus A cos theta naught, so it is a real quantity. Therefore, if you will take theta naught is smaller than pi by 2, okay, theta naught is smaller than pi by 2, then definitely this factor, that is square root of 1 minus 4 mgl cos theta naught divided by I1 a square, this must be greater or equal to 0, because only then C will be a real quantity. So definitely, as C must be real, we can take that this discriminant must be greater or equal to 0. And if this is greater or equal to 0, what does it mean? It means 1 must be greater or equal to 4 mgl cos theta naught divided by I1 a square. In other words, you can also say that this factor must be less than 1 or equal to 1. And this will be less than 1 only when I1 a square will be greater than 4 mgl cos theta naught. Only then this will be less than 1. Okay. So definitely in accordance with this condition, I1 a square must be greater or equal to 4 mgl cos theta naught. So I have written here, you can see that I1 a square must be greater or equal to 4 mgl cos theta naught. Okay. Now you have seen earlier, I have mentioned in equation A2 which we have obtained in first part of the lecture, that I1a is equal to I3 omega 3. You can change the page and you can see this result. Now when you will multiply this equation, see here, by I1 both sides, so this will be equal to I1 square a square, and that will be equal to 4 mgl I1 times cos theta naught. Okay. But I1 square a square, what will be that? That will be equal to I1 square a square, that will be equal to I3 square omega 3 square. So I3 square omega 3 square must be greater or equal to this 4 mgl I1 cos theta naught. And from here you can easily find the value of omega 3, and this will be greater or equal to 2 over I3 times a square root of mgl I1 cos theta naught. Okay. If you assume that the minimum value of this omega 3 is this much, okay, then you can see we can write omega 3 must be greater or equal to omega 3 minimum. Okay, omega 3 minimum. Actually, this result shows that precession at the angle of inclination theta naught of the symmetry axis is possible only if the angular velocity omega 3 of the spinning top about this axis is greater than or equal to its minimum value, which we have defined in this equation 5. Only when this condition will be satisfied, then the precession of this steady precession, you can say, of this top will take place. So for the steady precession of this top at angle of inclination theta naught, this condition defined in equation 4 must be satisfied. It means omega 3 must be greater or equal to omega 3 minimum, only then where omega 3 minimum is equal to this much, you can say that the steady precession will take place. Okay. Now obviously you know when omega 3 is greater than this omega 3 minimum, then C will have two values. You can see here in this condition this C will have two values. Okay. And actually for theta equal to theta naught, what are the frequency of oscillation? Actually that frequency of oscillation at this angle can be defined like this. This is phi naught dot. Actually in the first part of the lecture you have seen the result A4 where phi naught was defined, where phi dot was defined. Phi dot is equal to B minus A cos theta and divided by sine square theta. Now if you will put theta equal to theta naught in this result, then phi naught dot will be equal to B minus A cos theta naught over sine square theta naught. But we have assumed that this B minus A cos theta naught is equal to C. So this result is C over sine square theta naught. Okay. Now you have seen from this equation 3 here that C has actually two values, and from this equation when omega 3 will be greater or equal to omega 3 minimum, then the two values of C are possible, and so the precessional angular velocity, which is phi naught dot, will have two values, okay, corresponding to the two values of C. This phi naught dot will have two values. Okay. Actually among these two values one will be greater than another. Okay. So the greater value of C results in fast precession, and the smaller value of phi naught dot, that is called that will be the case of slow precession. And we denote this precessional velocity for fast precession and slow precession by the symbol phi naught f dot. Here f actually stands for the word fast, and phi naught s dot, here s is for slow. Okay. So you can say that if omega 3 is very large, then A is also very large, because you know I1A is equal to I3 omega 3. So definitely when omega 3 will be large, A will be also large. Okay. And if A is large, then what will be the value of this number? 4 mgl cos theta naught over I1A square. Since A is large, so A square will be much larger, and when you will divide this 4 mgl cos theta naught by I1A square, this will be a number much smaller than 1. It will be a number much smaller than 1. So if in this condition you will make the binomial expansion of this term, which comes in the expression for C. See here, in the value of C, apart from this multiplicative factor, the main factor is this. So we will simplify this expression under this condition that A is very large when omega 3 is very large. And you know that from binomial expansion that 1 plus minus x to the power n, this is almost equal to 1 plus minus nx, but when n is much smaller than 1. Okay. Sorry, not x is much smaller than 1. Here At the place of x there is 4 mgl cos theta naught over I1 a square. And in this condition you have seen that this is much smaller than 1. So we can make the first approximation in this binomial expansion, and we can write simply it equal to 1 minus nx. At the place of n there is 1 by 2. So this will be 1 plus minus 1 minus 1 by 2 into 4 mgl cos theta naught by I1 a square. Now 1 by 2 times 4, that will be equal to 2. So this is 1 minus 2 mgl cos theta naught over I1 a square. Okay. Now you can see when you will take this plus sign, okay, then your result will be what? This will be 1 plus 1, that is 2, and minus this factor. But in comparison to 2, we can neglect this second term. So in this condition you can say that this expression is almost equal to 2 only. And when you will take this minus sign here, then 1 minus 1 will cancel out, and this minus minus plus, that 2 mgl cos theta naught over I1 a square will remain. So this expression is either 2 or 2 mgl cos theta naught over I1 a square. Okay. So C will now have two values. When we will take this expression equal to 2, then we will get the larger value of C. And when we will take this expression equal to this much, that is 2 mgl cos theta naught over I1 a square, then we will get the smaller value of C. Okay. So what will be the values of C we can obtain from here? For getting the larger value, we will take this factor inside the square bracket equal to 2. So that will be equal to 2a sine square theta naught over 2 cos theta naught. Okay. And when you will try to find the smaller value of C, then you will take this expression inside the square bracket equal to 2 mgl cos theta naught over I1 a square. So you can see I have written here the two values of C. This is the greater value when we have taken this expression equal to 2, and so C is equal to a sine square theta naught over cos theta naught. And when we take the smaller value of C, then this C is mgl sine square theta naught over I1a. Okay. Now after getting the value, two values of C, you can find the corresponding values of this phi naught dot. For larger value of C, we will substitute here at the place of C in this expression this much. Okay. And when C is larger, we have fast precession, and the frequency or the angular velocity of this fast precession is given as phi naught f dot, which will be what? When you will take C equal to this much in the expression for phi naught dot, then your result will be a over cos theta naught. Okay. And this can be written as I1a over I1 cos theta naught. But you know I1a is equal to I3 omega 3 and divided by I1 cos theta naught. So I have written it here I3 omega 3 over I1 cos theta naught. Okay. And the frequency or the angular velocity for slow precession, that is phi naught s dot, when you will substitute this value of C in this expression, what will be your result? You can see this will be mgl over I1a. But you know I1a is equal to I3 omega 3. So instead of I1a, I have written it here. So in this way, you can see that we have obtained the frequencies or the angular velocity for the fast precession and the slow precession. But among these two results, this second result, that is the result for the angular velocity or frequency for the slow precession, is most important, because in practical, in most of the case we observe the slow precession, not the fast precession. Okay, when you will study in my forthcoming video the gyroscopic motion, then you will see that slow precession takes place in that very case. So this is this phi naught s dot is in fact generally observed. Okay, now actually now we will see the two very important result. You can see that when the symmetry axis of the top is at theta equal to theta naught, and theta naught is less than pi by 2, okay, and the top is rotating at the large frequency omega 3, then symmetry axis z dashed can precess about the fixed vertical axis z with two possible frequencies defined by equation 8 and equation 9. Actually, both of these frequencies, or you can say the angular velocities, are in same direction in this case. But when theta naught is greater than pi by 2, okay, then the fixed tip of the top is at a position above, and the top is hanging with symmetry axis with some angle from the vertical. And actually in this case, this phi naught f dot and phi naught s dot have opposite signs. That is, for theta naught greater than pi by 2, this fast precession phi naught f dot takes place in the same direction as that in the case of theta naught less than pi by 2. But the slow precession, that is phi naught s dot, takes place in the opposite direction as that for the theta naught less than pi by 2. So this is this depends on the value of theta naught. So in this way we have discussed the a particular situation of motion of the symmetric top, that is precession without nutation, and I hope you have clearly understand this. Okay, thank you very much.